So we are going to discuss first the electrolysis or electrolytic process. So in order to understand this, we need to first understand the concept called as the conductance or conductors. Now we are aware that there are two types of conductors. One is you call as electronic, the other is electrolytic. Now electronic conductors are also the metallic conductors, and electrolytic conductors are aqueous or molten solution of salts. So there are two types of conductors, as we all know. Now both are conducting the electricity, known as the conductors. Now when it comes to the metallic conductors, here we should understand that the charge carriers are the electrons. Now when it comes to the electrolytic conductors, here the ions carry the charge. This is the basic difference between these two. Now the next point, when you take the metallic conductor, there is no movement of the matter at all. That means when you take a copper wire through which the charge is passing, you are not expecting there the copper wire to move. Rather, only the electrons are subjected to the change of potential for which electrons are moving here and there. So there is no movement of the matter at all, whereas here there is considerable movement of the matter, that is the ions. This basic difference we should understand between these two. If I take a copper rod, I call it as the metallic conductor. If I take the aqueous solution of the copper ions, I call it as electrolytic conductors. Now when I see the other definitions attached to it, the other definition is what we call as conductance, and we need to know the similarity that we study in physics and chemistry here. As far as the conductance is concerned, we know it is the ease with which the charge flow through the conductor. Now when you take electronic conductor, you should see how easily the electrons are going from one place to the other. When it is electrolytic conductor, you should see how easily the ions are mobilized from one electrode to the other electrode, or from solution to the respective electrode. So we say clearly that it is the ease of what? The flow of charge. So as we know that conductance is the ease of flow of charge. If you are talking about electronic conductor, the charge is electrons, otherwise it is the ions. Now when I write the equation for the conductance, it is the reciprocal or inverse to the resistance. Now we know that if you take any specimen, say I have taken the metallic conductor whose length is L and cross sectional area is some A, and you know that R is, resistance is directly proportional to the length and inversely proportional to the cross sectional area. Therefore R is directly proportional to L by A, R equal to some constant into L by A. Here rho is called resistivity. Our interest is not R here, we are focusing on the conductance. Hence when I substitute the value, you are getting it as 1 by rho into A by L. When I am substituting the value of R here, you can see that 1 by rho into A by L. Now I will be replacing this term with Greek alphabet K, which is actually referred as kappa, Greek alphabet, and it is the specific conductance or conductivity. You can see here K or kappa is equal to C into L upon A. Now how do you define this K? It is nothing but the conductance of any specimen whose length is equal to 1 centimeter and cross sectional area is 1 centimeter square. What I mean to say that when these two values are 1, K is nothing but C. So you said that it is the conductance of a specimen which has the dimensions 1 centimeter and 1 centimeter cube. Hence the specimen will become the volume of 1 centimeter cube solution. So when I am transforming slowly into chemistry or chemical terminology, I say that this K, that is conductivity, is the conductance of any solution whose volume is 1 centimeter cube or 1 milliliter. So I am writing here, this K is conductance of solution 1 centimeter cube volume, because L equal to 1, A equal to 1 centimeter square, volume is 1 centimeter cube, and here L by A, which is going to be constant for a given cell, is referred as cell constant. So it depends upon now the distance between these two and cross sectional area of the solution which is lying over here, because we are not talking about the metallic conductor, we are talking about the solution. So we will be focusing on the cross sectional area of the solution which is dipped in which the electrodes are dipped. So cross sectional area of the solution and the distance between electrodes now is going to give you the exact volume of the solution which is under the electricity treatment for the electrochemical reactions. The conductance what we are talking about has been dealing only with the volume so far. Now what about the effect of the concentration on the conductance? Is it going to remain the same if I increase the amount of the salt, or it will differ? So in order to understand this important aspect, we need to understand what exactly is molar conductance and equivalence conductance. Now there is no huge difference between these two terms. One is represented by lambda m, I call it as molar conductance. The other one is lambda E, that is equivalent or equivalence conductance. The molar conductance is the conductance of all ions produced by 1 mole of electrolyte. You take 1 mole of the electrolyte and you measure its conductance, it is called molar. When it comes to this, the equivalent conductance is the conductance of 1 gram equivalent of the electrolyte. Now when I see the basic difference between these two and try to understand, what I will do is I will take 1 mole of electrolyte in 1 centimeter cube solution. I have taken 1 mole of electrolyte in 1 ml of solution. Since I have taken 1 mole, I call it as lambda m, and since I have taken 1 centimeter cube, I call it as K. Now I will write it as K into 1 centimeter cube. Now suppose I have diluted this. Suppose this solution is diluted to 1000 ml. Diluted to 1000 ml. Now you know that upon dilution the moles or equivalents are not going to change. So what is going to change is only the concentration. So when I have diluted this, even the volume although becomes 1000 ml, the amount that is present will remain as 1 mole and it will still remain as lambda m. But this K term will become how much? K into 1000, because 1 centimeter cube constitute K, 1000 centimeter cube will become how much? Now this is not going to change because moles are not going to change upon dilution. Now when I make it say to 5000 ml also, you all know that lambda is not going to change, but this will become K into 5000 centimeter cube. Now what I mean to say, that this lambda is affected by this volume. So here when I am writing the parameter which is coinciding these two, I will write it as lambda E equal to K into volume of solution having 1 mole of electrolyte. Now this is the relationship between lambda and K, whether it is lambda m or lambda K. Since I am dealing with lambda m, I am writing it as lambda m. This is the relationship. Now suppose I have a solution is C1 mole per liter. The concentration of the solution that you have is C1 moles are present in 1 liter. That is 1000 ml of solution is C1 mole. So you say that C1 mole when are present in this much ml, what will be the volume of the solution which has 1 mole of an electrolyte? So it is turning out to be how much? 1000 upon C1. So when I am substituting here, you can see here the volume of solution which is having 1 mole. From this relationship, if the concentration of your solution is C1 mole per liter, you are writing at a lambda m equal to K into 1000 upon C1. What is C1 here? Mole per liter. Suppose if you want it in a other unit, that is mole per meter cube, you are going to write this 1000 get cancelled, mole per meter cube. So this is the relationship between the lambda and K. Now when I talk about the relationship between lambda E and lambda M, I can use this terminology, where what I will do is, I will write that for lambda E also, just what will become? C2. Say the concentration of the solution when I am expressing in normality or equivalent per liter is C2 equivalent per meter cube. Now you understand the relationship between equivalents and moles or normality. You can see here normality equal to molarity into n factor. What is n factor here? For a given salt, it is the number of moles of electrons absorbed or released during a redox reaction. So when I am substituting here that value, you can see what this will become. Lambda E is equal to K, that is specific conductance, divided by C1 into n factor. You know that this term is lambda m divided by n factor. What is n factor here? The moles of electrons absorbed or released during the redox process. So here we have to focus or emphasize on 3 relationships. One is lambda m and K, the other is lambda E and K, the third one and the most important one is lambda E and lambda m.